Hello and welcome to our video on the synthesis of biodiesels. So with regards to Year 12 chemistry, there's two main biofuels that you need to know. So you can think of the biofuels as the main overarching headline, and then within the biofuels you need to know about ethanol, and then you need to know about biodiesel. So today, this is the one we're going to be covering today. We have a separate video on ethanol, which I recommend you watch. Those are the two main biofuels that you need to know. With regards to the agenda for today, we'll be starting on a brief introduction on what biofuels actually are, because it's pretty important that you understand that. Then we're going to be delving a little deeper into biodiesel. So firstly, what is a biodiesel? Secondly, how do we make it? Going through the whole process here. And then thirdly, going over some advantages and disadvantages of using biodiesels compared to normal diesel. So with regards to these biofuels, such as ethanol and biodiesel, it's important you wrap your head around why they're actually important in the first place. So currently, what we're doing is we have fossil fuels that we dig up out of the ground and we make octane out of that, and we essentially burn the octane in our cars, which produces CO2. So we're digging up a non-renewable resource, putting it in our car, burning it, and we're not recycling it. And this process just keeps on and on and on, right? However, with biofuels or carbon neutral fuels such as ethanol and biodiesel, we can actually source them from renewable resources, such as for ethanol, we can source it from sugarcane, and we have a whole video on this. And from biodiesels, we can source it from animal fats or recyclable, or even like restaurant oils. And I'll just write oils here. So basically, what we're doing is, instead of digging up a non-renewable resource, we're using a renewable resource, which I've symbolized by the tree. So with ethanol, you could get it from sugarcane, for example. You use a process such as fermentation, and then you make the biofuel. We then put it in our cars, and we burn it. Effectively, what's happening is the carbon dioxide that's released by the car goes into the atmosphere, so that's the atmosphere. However, that carbon dioxide is then reabsorbed by the renewable substance that we're making the fuel from. So it's kind of like a loop. So in this way, ethanol and biodiesel have the potential to be carbon neutral fuels. So we're not just digging up non-renewable substances. So they solve that problem in the future. So before we start our conversation on biodiesels, it's important we understand what diesel actually is, because that's what you find at regular pump gas. So basically, diesel is a long hydrocarbon chain molecule. So it has about 8 to 21 carbons in it. It doesn't mean that all of the molecules in the diesel will have exactly the same number of carbons. Think of it as more of like a mixture. Biodiesel has a similar chain length of about 8 to 21 carbons. However, the key is it has an ester functional group, and that's where the word FAME comes in. So we can collectively call biodiesels fatty acid methyl esters. That's what they're collectively known as. We make them through a process called esterification, and we can source them from theoretically any triglyceride. So a triglyceride, as you may recall on our video on saponification, has the glycerol backbone and the 3 fatty acids coming off it. So examples of triglycerides could be corn, palm, coconut, sunflower, or peanut oils. And as you might have been able to tell, the highest yield that we can get out of making biodiesels is by recycling restaurant or household oils, right? And biodiesels, as we said in the previous slide, are renewable, clean-burning diesel replacements. The highest yield is, unlike ethanol, they don't require too many modifications from current diesel engines. So now we'll start our conversation on how do we actually make the biodiesel. So the first step is something we know as feedstock treatment. So once we get the recycled oil from houses or restaurants and so forth, we need to process it to remove a couple of things. We need to remove dirt, charred food, and water, because as you can imagine, these are recycled oils. They're not going to be 100% pure. However, in this process, we need a couple of things out of that oil. So the first thing we're going to do is filter out. So literally filter out the dirt, charred food, and water. So as you'll be able to tell, water will become a slight recurring theme in the future. So for this reaction, we really don't want any water to be present. So as you may recall, triglycerides, we take them through a esterification reaction to make biodiesels. However, in the presence of water, the triglycerides will undergo a saponification reaction to make soap instead of biodiesel. That's a high yield takeaway. So you may have covered saponification. We don't want that. We want esterification to make biodiesels. So we got rid of the charred food, we got rid of the water by drying the oil, and we've got rid of the dirt. So those are three of the main things. However, one other thing that's pertinent is the presence of free fatty acids. So we'll begin our discussion on that. So if you're owning a biodiesel factory and I give you a ton or a tub of recycled oil or feedstock, right? That's what we call it typically in industry. Feedstock. That oil is not going to be 100% triglycerides. It's going to have some free fatty acids, right? However, for this process, all we want is the triglycerides. So we can't afford to have any free fatty acids floating around, not connected to any glycerols. We just want the triglycerides that are triglycerides, really. So we need to do two things. Firstly, find how much of the oil is triglycerides, and we do that by undergoing a titration. So we use titrations when we have an unknown concentration of something. So we undergo a base titration because it's a free fatty acid to evaluate the concentration of the free fatty acids. The next thing we do is convert these free fatty acids that are present in the feedstock to make extra biodiesel. And I'll show you in the next slide how we do that. It's pretty clever. So after I've found the concentration of the free fatty acids, I can equilibrate the amount of moles of free fatty acids I have in my oil. So I'll draw up the oil container again. So I can find exactly how many moles are in that oil. What I then do is add a 1-to-1 ratio of alcohol in the presence of a base catalyst, which is typically sodium hydroxide. Then what I can do is make biodiesel or fatty acid methyl esters and water. And recall that the alcohol is usually going to be methanol. There's not a great emphasis on knowing this for the exam. This is just for your interest. Especially with this process, just have a general idea on the whole process. There's no real need to memorize the whole process and fixate on small details. This, however, was just for your interest. Now where we're at is we have a tub of hopefully pretty pure triglycerides. So next we need to actually undergo the production method, which is esterification. So where did we start? We started with recycled oil, we purified it, we treated it, and now we should have a tub full of a pretty pure liquid containing only triglycerides. So now we need to make some biodiesel out of it. So what we do is a process called esterification. I'm going to repeat myself because it's a pretty important dot point in the syllabus that you know this process is esterification. For esterification, you need a couple of things. So firstly, you need an alcohol. Which typically we tend to use methanol or ethanol, especially methanol because it's really cheap. However, we can use ethanol in the future to make this process extra green friendly because, as you know, we can source ethanol from sugarcane and fermenting sugarcane. One other thing we need is a base catalyst. So the base actually acts as a catalyst in this reaction, and typically any strong base such as sodium, potassium hydroxide will work, and those are actually the two that we tend to use, especially for their cost. So that's another important consideration in this industrial process. And one other note, I did say that water would be a recurring theme, and as you can see, it clearly is once again. So we need to make sure that the reaction vessel is sealed and dry, especially dry is the key word, because as I said, the presence of water is going to direct the reaction to more saponification than esterification. We don't want to make soaps, we want to make some biodiesel. That's the key. So essentially, this is the reaction that's occurring. So there's a couple of things that we need to go over. So firstly, on the left-hand side, we have the triglyceride. And we have the glycerol backbone and the tri part, which is the 3 fatty acids. So 1, 2, 3, 3 fatty acids connected to that glycerol backbone. That's your triglyceride. Then for this reaction, we need exactly 3 moles of ethanol or methanol or whatever alcohol that you choose for this reaction. The base acts as the catalyst, and essentially what happens is it cleaves off each of these fatty acids off the glycerol backbone. So what you're left with is glycerol. So this is glycerol, or glycerine if you're American, and you have 1, 2, 3 biodiesel molecules that we can use. So as always in chemical synthesis, there are some reaction conditions that we need to go over, 3 in specific, and we'll cover them really quickly. With the first one, what we tend to do is before we dump, so if I take you back to this reaction, you might think that we have the triglycerides, we add the alcohol, we then add the catalyst, and then we get the reaction products. But however, in real practice, that's not exactly what happens. What we tend to do before we add anything is mix the alcohol and the base catalyst together. Sorry, if I grab my pen, the alcohol and the base catalyst together to form what we know as an alkoxide. Then we add the triglycerides to this alkoxide and the reaction proceeds. So that's a really good way of increasing yield. For the next topic of conversation, I'll bring your attention down the bottom here. So with regards to temperature, we tend to use a temperature of roughly 50 to 60 degrees Celsius. However, there's 2 points for why we do that. So with regards to this reaction, it's an exothermic process. So if I grab my pen again, exothermic process. So plus heat at the end. So always remember, esterification reaction, exothermic process. If we increase the heat of this reaction, that's a change that we've imposed on a system that's otherwise in equilibrium. The system is going to shift in a way to minimize the impact of that change. So in this case, it would be a right to left shift. So if we have really high temperatures, what it's going to do is lower the yield of the holy biodiesel, and we don't want that. However, increases in temperature, as I'm sure you're well aware, increase the reaction rate. So it's a bit of a fine balance. However, unlike the other processes or other chemical synthesis that we've discussed, we have a huge limiting factor. So methanol or ethanol has a boiling point of about 68 degrees Celsius. So we can't afford to have a temperature that high anyway. So what we tend to do is settle for a temperature of roughly 50 to 60 degrees. So we get a nice yield and a nice reaction rate, so it's not too slow. The second dot point is actually quite intuitive. However, we will need the reaction to look at it in a little more detail. So with this, we have 1 mole of the triglyceride reacting with 3 moles of the alcohol to make 1 mole of the glycerol and 3 fatty acid methyl esters, or 3 moles of the biodiesel, right? So basically, the triglyceride and the alcohol are in a 1 to 3 mole ratio. Now, we could do this. However, to maximize the yield, we could utilize Le Chatelier's principle. We could add the alcohol in excess or add way more than 3 moles. Basically, that would be a change or imposing a change on a system that's otherwise in equilibrium. The system is going to respond in a way to minimize the impact of that change by shifting in a direction to obviously minimize the impacts of that change. So that is going to be from a left to right direction to use some of that excess alcohol and make more fatty acid methyl esters. However, we run into a problem. If we add too much alcohol, it makes it really difficult to separate at the end, because at the end, we'll have a mixture of a lot of alcohol and a lot of fatty acid methyl esters, and that's not what we want. It makes it really hard to purify this product here. What we tend to do, they've worked it out and they've realized the ideal ratio is for every 1 molecule of triglyceride that you have in your big tub of purified triglyceride, you add exactly 6 moles of the alcohol, and combine these 3 reaction principles give you a pretty good yield of up to 98%. So now that we've made the biodiesel, we obviously have some leftover reactants, and we also have glycerol. So we have, at the end of the reaction, we have glycerin, the base catalyst, we have the triglycerides, the biodiesel, and the alcohol. However, out of all those things, all we want is that. To get the biodiesel, we need to do, so at the end of the reaction, we have a couple of things. We have our 2 products, we have the glycerol and the biodiesel, and we have some reactants that are left. So we have the catalyst, we have the alcohol, and we have the triglycerides. However, out of all those things, the only thing we want is the biodiesel. So we need 2 processes to get just the biodiesel. We separate and then we purify. So in this separation process, you don't need to know these 2 into too much detail, just know the basics of it. So what we do is we rely on the differences in density. So you can either let the mixture sit or centrifuge to speed it up, but what actually happens is over time you get 2 layers. You get an upper phase or an upper layer and a lower layer. So in the upper phase or the upper layer, you'll have mostly the triglycerides and the biodiesel. Think about oil floating to the top of water. And at the bottom, you have the catalyst, you have the excess alcohol, and you have the glycerin. So the next process, what we would do is we would essentially just tap that off and we would recycle those components to use back in the industrial making of the biodiesel. So we've tapped off the lower phase and the upper phase contains mostly biodiesel. However, this isn't good enough for a standard of fuel. So we need to have a purification step where we make this biodiesel to a tip-top standard. There are a couple of things that we do. The first is a washing step where we essentially run water through the fuel, right? And that will hopefully get rid of the methanol, the catalyst, and the glycerin, because those three things are water soluble. We basically add water, let it settle, tap it off, add water, let it settle, tap it off, if that makes sense, because this will always float to the top of any water that we add. However, the methanol, the catalyst, and the glycerin will dissolve in any water that we add. So in the previous slide, I said that on separation, you'd get an upper phase and a lower phase, and I showed you two distinct colors. However, in actual practice, you would get some molecules or some lower phase molecules in the upper phase. So you would theoretically get some alcohol, glycerin, and base catalyst in that upper phase of mainly the biodiesel. So that's why we undergo the washing step. Another step that we undergo is adding any acid to neutralize the base catalyst. After that, we add another washing step. So that's adding water, letting it settle, tapping it off, adding water, letting it settle, tapping it off. The last thing that we do is dry it. So that last process gets rid of any excess water that we have. So we're hopefully left with 100% or near about 98%, sorry, biodiesel. And this is just a quick schema showing you the whole process in industry. So to answer questions, it's important that you know some of the advantages and disadvantages of biodiesel. So we run through some of those now. So with regards to the advantages, we did touch on some of them earlier. However, we'll cover them a bit more systematically now. So number one, it's renewable. We can make it from recycled vegetable or vegetable oils or animal fats that we would otherwise throw in the bin and that would contribute to landfill. So we're getting a source of energy or a source of fuel out of that. It's got low toxicity, which is good. And thirdly, which is amazing, is that it is really degradable. So that comes in handy if we have a spill. So think of like a large ocean tanker spilling oil into the ocean. If that is biodiesel that it spills, it'll be a lot more easy to clear up because it degrades a lot more easily. Once we actually burn the fuel, it has a lower level of contaminants that it releases into the atmosphere, such as carbon monoxide, for example. It doesn't release that much sulfur dioxide, so that relates to the concept of acid rain. And it's got a higher flash point of about 100 degrees Celsius, so it means it's readily combustible. So with regards to biodiesels, there's some distinct disadvantages. One of those that it shares with ethanol is that it has a lower caloric value compared to its counterpart, diesel. So biodiesel, for the same molecule, has lower caloric value than diesel. So what does that actually mean? Essentially, you need to burn more biodiesel to travel the same amount than you would with diesel. So a cost comes into effect, supply comes into effect, especially on a mass scale. That's an important consideration. Another thing is it has a higher freezing point than diesel fuel, which it'll be great in a country like Australia where that's not really an issue. However, if you're in a colder temperature, such as Alaska, for example, that might be a bit inconvenient, right? It's less stable, so the fact that it's more degradable is great for biofuel spills. However, for long-term storage, so you can't really store it for more than 6 months. That's where the degradability has both an advantage and a disadvantage. One other thing, although we can theoretically use it in our current diesel engines, over time you'd get a massive degradation of plastic and natural rubbers, especially in the gaskets and hoses, so you would need to replace those components with Teflon-based components. Don't remember the specifics of all this, just know that over time it's going to degrade the plastics and rubbers, you need to replace them. So in the previous slides, we covered the base catalyzed method of esterification to make biodiesels. However, for your syllabus, it's important you at least know of the presence of a lipase catalyzed method for making biodiesels as well. So essentially what lipase is it's a biological enzyme, and I'll say slash catalyst, but it's mainly an enzyme. Essentially what lipase is doing is it's doing the same job as what the base catalyst would do in the previous method that we discussed. However, with lipase, it works a bit differently. So it's a biological enzyme, and you can think of it as kind of like an actual organism that's cleaving at each step one of these fatty acid chains at each step. So over time, what you're going to get is the same products. You'll get the same 3 fatty acids, and you get the glycerol at the end. However, you don't use a base catalyst, you use lipase. That's the only thing. Sciences it's not really something that we can do in practice or in industry just yet. We're trying to make the lipase as tolerable and as efficient as possible. However, it's just not there yet. So with this process, there are a couple of key dot points that you need to know. So firstly, we do get pretty good yields out of it. However, on an industrial scale, it's just not there just yet. Another thing, it's very sensitive to high free fatty acid content. So in our original process, we went through the feedstock treatment stage, and we were trying to get rid of as much of the free fatty acid content in our recycled oil tub as much as possible, right? With the lipase catalyzed method, that's a big issue. You need to get rid of most of the free fatty acids. However, for the base catalyzed method, that's not really too big of an issue. One other point you need to remember is methanol is toxic to the lipase catalyst. So we can't use methanol. A substitute that we can use is methyl acetate. Don't really worry about the reasons why. Just know that methanol is toxic. Methyl acetate is the substitute that we use.